Hello! In this video, we will be discussing three topics regarding advanced mathematics. These are Fourier series, matrices, and determinants. We will discuss their definitions and we will work some examples regarding these topics. Okay, so let's start first with Fourier series. Okay, but before that, we should review some topics first. So let's review first periodic function. A periodic function is a function that repeats its values in regular intervals or periods. To visualize it, we have a figure here. Let's assume that this is the initial position of the initial point of the graph. So after a certain interval or period, you can see here it returns to its initial value and then it repeats so forth and so on. So that interval or period is very important in determining the periodic function itself. Okay, let's just note that. Okay, so here's an example of a periodic function. So let's define this function according to this graph. Okay, as you can see here in a triangle wave, it repeats its values after 2 pi intervals. How can I say that? Okay, let's assume the initial point is in negative pi. Okay, and then at what point I see again when f of t is pi? Where? So as you can see here, when it is on the pi, on the x, or sorry, in the t axis. Okay, so we could say here, the distance between negative pi and pi is 2 pi, to put it simply. Okay, so and it just repeats and repeats this type of pattern every 2 pi intervals. Okay, so we could define this function f of t is equal to negative t from negative pi to 0, as you can see here in the graph here. And then it's f of t is t from 0 to pi. Okay, so more simpler, f of t is equal to the absolute value of t from negative pi to pi. If you could recall the figures of different graphs, you know that the f, uh, f of t is equal to absolute value of t pertains to like a v figure. So as you can see here, we have a v here from negative pi to pi. Okay, so for the function itself of a periodic function, we could say that f of t is equal to the f t plus 2 pi. So 2 pi here is the interval. Okay, we could say that the 2 pi is the interval according to the figure itself. Okay, so I hope that's clear. Okay, so another thing we need to review is about odd and even functions. Start first with even. A function is even when f of x is equal to f of negative x. Okay, so as we can see here in the figure, okay, this curve is defined as f of x is equal to x squared plus 1. Okay, so let's assume, or let's put the x is equal to 1. Okay, so what is f of 1? 1 squared is equal to 1 plus 1. Okay, so it is just 2. Okay, so what is then f of negative x? It's just f of negative 1. Okay, so f of negative 1 is just negative 1 squared. What is it is also 1 plus 1, and then we get 2. So this function is an even function because f of 1 is 2 and f of negative 1 is 2, satisfying this condition. Okay. So there's an easier way to analyze the function. There is symmetry in the y-axis, underlined here. So as you can see here, we have the y-axis here. And then look at the right side of the curve. Okay? What can you see on the right side and in the left side? It's just like a mirror image. Okay, so if you put the whole curve or the graph or the function, and then slice. It's just the y-axis is slicing through it, dividing it evenly. Okay, so that's what we need to analyze. Okay. Another thing we need to note is that a cosine function is an even function. Okay, so how is that? Okay. So we have here a figure of the cosine wave or the cosine function. Okay, so as you can see here, let's try to visually analyze this first. Okay. So here's the y-axis, and what you can see, it just sliced or dissected the whole wave into equal halves. There's symmetry in the y-axis, so it's just like a mirror image of the right side and the left side. Okay. So you could, it's just easy as that. Just visually analyze it. Okay. Okay. Next, a function is odd when f of x is equal to negative f of x, or in simpler terms, there is symmetry in the origin. So we have the figure here. The curve f of x is equal to x cubed minus x. Okay, so what we will be looking here is that in a certain point, there is equal distance of that point from each other. Okay, so as you can see here, so let's try first to let's solve. Let's try. Okay, so let's appoint the value of x is equal to 2. Okay, so f of 2 is equal to 2 cubed minus x, 8 minus 6. Sorry, 8 minus 2 is equal to 6. Okay, then f of negative 2, we will get negative 2 cubed is negative 8 minus negative 2 will have negative 6. Okay. So as you can see there, let's assume that this is negative 6 on the figure. Let's replace that. I'm so sorry. Let's replace x here by 6 and negative 6. Negative 6 and 6. So what can we see here? Okay. There is equal distance from the origin. Okay. So the distance of f of x is 6 units. And the distance of f of negative x is negative 6. So it satisfies the condition stated earlier. Okay. So you can also see the symmetry in the origin. Another thing you can see, or another way to analyze this graph. So let's try here the right hand side of the wave. So let's try to rotate it 180 degrees. So what will happen? It goes to the, it appears to be similar to the left side. So in my way, so I think that's another way to see an odd function. Okay, so a thing to note here is that a sine function is an odd function. How is that? So let me just erase markings here so that I can show you the sine function clearly. Okay, so here is an image of a sine function. So visually first, as you can see here, if you rotate the right hand side 180 degrees, it will just be like the left hand side. So if you're getting what I'm saying. So to put it in technically, so here is pi over 2, right? Pi over 2. And then here is negative pi over 2. So look here. So f of x here, or when f of pi over 2 is equal to 1. On the left side, f of negative pi over 2 is equal to negative 1. So as you can see in the figure earlier, they have the equal distance from 0. Okay? So we could say that a sine function is an odd function. Okay, so now that we know odd and even functions, so I need to show you when multiplying odd and even functions. Okay, so when you multiply an even function by an even function, you'll get an even function. So, and if you multiply an odd function by an odd function, you'll get an even function. And if you multiply an odd function by an even function, you'll get an odd function. So let us now discuss the concept of Fourier series. Okay, so consider a square wave as you can see here in the figure. Okay, so can we attain this graph using sine waves? Okay, so let's find out. So let's start with sine x. As you can see here that the wave follows the pattern of from up, down, such as a square wave. However, it does not look like a square wave. So, but what if we add sine 3 of x over 3? Okay, so when we add that to the characteristic of sine of x, you can see here that it somehow followed the pattern of the square wave. Okay, but it does not look much of a square wave. However, what if we add sine 5 of x over 5? Okay, so as you can see here, it comes nearly again as a square wave. However, not very near. But somehow made it made the sine wave look more like a square wave. So, as you can see here in the figure, using 20 sine waves, we get from sine of x to sine of 39x all over 39. As you can see that it follows the odd pattern because sine of x is an odd function. So we need to use odd coefficients. Okay, so as you can see here, in the 20 sine waves, first, it almost nearly follows the pattern of a square wave. Stammering pa. So, using 100 sine waves, as you can see here in the figure, it's almost or nearly as a square wave. So the idea here is that when you add the sine waves or that pattern infinitely, we get a square wave. So that is the idea of a Fourier series. Okay? So the formula for a Fourier series is given here. F of x is equal to a naught over 2 plus the summation from n equals 1 to infinity of a sub n cosine n pi x over L plus b sub n sine n pi x over L. Okay? Where f of x is the function we want. In our case earlier, f of x is the square wave. Sorry, that's a v. L is half the period of the function. Okay? A naught, a sub n, and b sub n are the coefficients, which also have their corresponding formulas, as you can see here. Okay. A naught is equal to 1 over L times the integral of f of x dx with the from negative L to L. Okay. A sub n is equal to 1 over L times the integral of f of x cosine n pi x over L from negative L to L. Okay. And b sub n is equal to 1 over L times the integral of f of x sine n pi x over L dx from negative L to L. Okay, so here's an example on how to solve a Fourier series. Okay. Let f of x be a function of period 2 pi such that f of x is equal to x squared over the interval from negative pi to pi. So it means that the function f of x equal to x squared repeats, or its starting point is from negative pi, then goes back to its original value or its initial value after pi at pi, I mean. So it is given that the period or the interval is 2 pi. Okay? So A, sketch a graph of f of x in the interval from negative 3 pi to 3 pi. B, show that the Fourier series for f of x in the interval from negative pi to pi is here. Pi squared over 3 minus 4 quantity cosine x minus 1 over 2 squared cosine 2x plus 1 over 3 squared cosine 3x minus so forth and so on. Okay, so for A, we need to graph the function of f of x equal to x squared from negative 3 pi to 3 pi. So from the initial condition, 2 pi, from negative pi to pi, as you can see here, you already have the interval of 2 pi. So we just need to extend that from negative 3 pi to 3 pi. Okay, so how do we do that? It's just simple. Okay, so from negative pi, let's move another 2 pi intervals. Okay, so from negative pi to negative 3 pi, that's an interval of 2 pi. So it's just another curve. Same as from pi to 3 pi. It's just another curve. Okay, so that's it. It's just that. Okay, so let's solve first for a naught because that's the easiest part. Okay, so we have a naught is equal to, from the formula earlier, we have 1 over L times the integral of f of x dx from negative L to L. So we have already substituted L there. So our L is half the interval. Our interval is 2 pi. So our L is just pi. Okay? So substituting the f of x here, we have 1 over pi times the integral of x squared dx from negative pi to pi. Okay, solving that, it's just easy. So feel free to pause the video to see the solution. And we have a naught is equal to 2 pi squared over 3. Okay. So now we need to solve for the a sub n. Okay. So a sub n is equal to 1 over pi times the integral of x squared cosine nx dx from negative pi to pi. So what happened to the formula n pi x over L? So our L is equal to 2 pi. Oh, I'm so sorry. It's just pi. So n pi x over pi. So pi is just cancelled. Okay, so just so we're clear. Okay, next, we integrate this by integration by parts. Okay, so we get x squared sine nx over n, and with the limits from negative pi to pi, minus integral of 2x sine nx over n dx from negative pi to pi. Okay, so solving that, again, so in the first term, we apply the limits here. As you can see, pi squared sine n pi minus pi squared sine negative n pi. Okay, so minus 2 over n times the integral of x sine nx from dx from negative pi to pi. So we just need to notice this, sine n pi and sine negative n pi. So going back to the graph earlier, you may reverse or recap the video if you want to see the graph. We can see that the interval is just jumping by pi. Okay, so whatever the value of n is, from 1, 2, 3, 4, 5, 6, it will still just be pi and negative pi. Okay, so what does that mean? So that value will always be 0. So that's why it's 0 here. Okay, so 0 minus 0. So the first term will just be cancelled. Okay, so we get here at the end of the row negative 2, or I mean the end row, sorry, negative 2 over n pi times the integral of x sine nx dx from negative pi to pi. To solve that integral, we need to use integration by parts again. So we have the result here. Negative a sub n is equal to negative 2 over n pi times quantity x times negative cosine nx over n with the limits from negative pi to pi minus the integral of negative cosine nx over n dx from negative pi to pi. Okay, so simplifying it, we have the following here. Okay, so we need to analyze first, again, the integral of cosine nx dx from negative pi to pi. Okay, so the result here, applying the limits, we have sine n pi minus sine negative n pi. So from earlier, the last slide, it just results from 0 minus 0, with which becomes 0. So as you can see here next, it just becomes 1 over n times 0. Okay, so also here in the next part, we applied the limits. So negative 2 over n pi times negative 1 over n times pi cosine n pi minus negative pi cosine negative n pi. Okay, so we first need to analyze this. Why did it become negative 1 raised to n? Okay, it is because when we put, so here we have cosine n pi. So what if n is 1? So cosine pi is negative 1. So what if n is 2? Cosine 2 pi is 1. So it is just as simple as negative 1 raised to n. It's just the same pattern. Okay, so it is just substituted as that. So we have here, simplified from cosine n pi, we have negative 1 raised to n. And I need to also note that it's just the same as negative n pi. Okay, why? Okay, so negative 1, or I mean negative pi, is just equal to negative 1. Okay, it's just the same because from negative pi, it's just from converted to degrees, it's just negative 180 degrees, which just results to negative 1. Okay, so it's just the same. So that's why we have here pi times negative 1 raised to n plus pi raised to negative 1 raised to n. Okay, so finally we have here negative 2 over n pi times negative 2 pi over n times negative 1 raised to n. In further simplification on what we found earlier, we now have 4 over n squared times negative 1 raised to n. Okay, so we could simplify that expression into here. A sub n is equal to 4, positive 4, over n squared if given that n is even. Okay, so that's self-explanatory. And negative 4 over n squared if n is odd. Okay, so we need to keep that in mind. So solving for b sub n, we have we have 1 over pi times the integral of x squared sine nx dx from negative pi to pi. Okay, so we need to discuss the topic about even and odd functions here. So it is said that if you integrate an odd function with the limits from negative L to L, or from a negative value to its positive value, it becomes 0 because it just cancels out. Okay, so let's consider here a sine wave. Okay, so if we integrate here from here, okay, so from here to here, you can see that this negative value cancels the positive value, so it results to 0. Okay, so feel free to pause to verify the solution for this, but we will end up of p sub n is equal to 0. Now, substituting the coefficients we solved earlier to this formula. Okay, so we have a naught is equal to 2 pi squared over 3, and a sub n has 2, 4 over n squared if n is even, and negative 4 over n squared if n is odd, and b sub n is equal to 0. Okay, we saw that earlier. So we have here the table n and a sub n. Okay, so if n is 1, we have negative 4 times 1. If n is 2, we have 4 times negative 1 over 2 squared, and then it goes so forth and so on. Okay, switching from negative, negative, positive, negative, positive, and then the denominator is just the n squared. Okay, so we can factor 4 out. So we have here f of x is equal to is equal to 1/2 times 2 pi squared over 3. We just cancel 2 minus 4 quantity cosine x minus 1 over 2 squared cosine 2x plus 1 over 3 squared cosine 3x, and so forth and so on, plus, since b sub n is equal to 0, it's just 0 plus 0 plus 0 infinitely. It's just still 0. Okay. So finally, we have f of x is equal to pi squared over 3 minus 4 quantity cosine x minus 2 squared cosine 2x plus 1 over 3 squared cosine 3x minus 1 over 4 squared cosine 4x plus, and so forth and so on. So we now solved b. We proved that the Fourier series for that periodic function is equal to this. Okay, so we represented that periodic function, okay, earlier, f of x is equal to x squared from interval with interval of 2 pi is equal to this. Okay. Okay. So that's our topic for Fourier series.